So, welcome. Uh, Almost the end of the semester, and we appreciate it that you come in the storm. And welcome. This is lecture 12 out of 13. We're going to talk today about allocations and real time as much as we have time during the talk. So we start with allocations. We'll start with some basic notions and techniques. Dudley and Bohm's allocators were the first tradition, like classical allocators, and then we'll talk about more advanced techniques. And we should we should differentiate between allocators that should work with garbage collection and allocators for malloc and free. And somehow they advanced in parallel lines, different researchers or practitioners that developed them, different techniques used, and we'll talk about the differences. Allocators for GC, if you have a garbage collector running, then it influences how you do allocation. So if you do copying, you basically don't need to worry about anything. You just bump a pointer, like you copy everything to the beginning of the second part of the heap, and then you can allocate by bumping a pointer until the space is complete, and then you do a garbage collection, you move to the second space. So with copying, there's nothing to say much. And with sweep, you go through sweep and you have, you're like taking all the free spaces and putting them maybe in a free list, maybe in other structures. We'll talk about that. Reference counting and manual free, they just, so in manual free, you just get a piece of empty space that you're told that it is free now. Either the user says it or you have reference count 0. And then you have to let the allocator know that it can use it for future allocations. So this is how it goes. So allocator usually very naturally is measured by speed of allocation, how much time it takes to allocate, how much time it takes to free an object. All of that is very clear. Fragmentation, we'll talk about that soon. Cache conscious, so you should be aware that there is a cache, there is locality. You should do good things for that, and the program will run faster with your allocations. And like I said, the algorithms were developed initially separately between garbage collector and manual allocations, but I think recently, they basically merged. Okay, so what is fragmentation? Fragmentation in general is the inability to reuse memory that is free. And generally it's because you have these small holes and you cannot use them for allocations. There is a bigger object and it doesn't fit in the holes that you currently have. So how bad it is, it depends on what I'll allocate in the future. So it's really hard to define if a current heap is fragmented or not. It depends on what will happen. So I cannot say too much about it. There were all kinds of attempts to define fragmentation and whether a heap is fragmented or not. They were not very interesting. I will not discuss that. But it is true that you can make a heap less or more fragmented. And we'll talk about this. So external fragmentation is that you have holes between objects and they're too small to allocate. Internal fragmentation is that you have fixed, like the smallest area you can allocate in, and then what you actually need is smaller than that. So you allocate a space for an object, but you don't use all the space you allocate. Here is a drawing. So if I want to allocate this larger object in these smaller holes, then fragmentation doesn't allow that. And if I have a minimum possible allocation sizes, which are like that, maybe I have a fixed size spaces to allocate in, and then comes a smaller object, then I don't use some space. And this is also fragmentation. So this is internal fragmentation. Um, in general, I want you to know the basic notions, and we'll talk also about algorithms, but the really basic notions is best fit, first fit, free list, segregated free list, and boundary tags. Was there in any other course, did you talk about best fit and first fit? Which course? Adam. Okay, cool. Okay, so best fit is you allocating the smallest free space that's available for your object. And the naive implementation is just you search for it, right? And then this will take a lot of time. You may search the entire heap and it's unacceptable. So many times people that first look at best fit say it's not good, it's very inefficient, you cannot use it. But actually, the implementations are not like that you're looking for a place to put your objects. You index all the free spaces. You could use a binary tree if you like to look for the space you need, or you could use what is usually done is a list of available blocks for each possible size. So we'll talk more about this because this is really used in practice. So I'll not elaborate now. But the thing is there is a difference between the policy, you say best fit. I want to put in the smallest space that could fit my object, and saying how you're going to implement the policy. So the policy is not inefficient. Your implementation can be efficient or inefficient, but the policy is just best fit. Implementation could be more or less efficient. Okay, in practice, it exploits much of the used whole. So you use your heap. There's a fragmentation is good, like you're not getting too fragmented. But if you take the smallest space that fits your object, the remainder that you don't need is going to be small, usually. So if you have a space of size 20 and you allocate 18, then the 2 bytes remaining will probably not be used for anything later. So you get this waste, but in general, it's not serious. In practice, it is used. First fit, you allocate in the first place you can. If there's a good enough space, you go over the spaces. The first one that fits, you use. And so this typically, you can go in any order you like between the free spaces, but usually you do it in address order. And it can be whatever you want, free list order. Maybe you add stuff to the free list in various ways, and eventually you get some order on the free list, and you look in the free list for a good enough space to allocate. And once you find a slot you can allocate in, then you split it, you take whatever you need, and the rest you leave in the allocator's hands, whatever way it keeps the object. And if it's a free list, you leave it in the free list, and then you just use that. So usually in the beginning of your free list or whatever way you go over the spaces, in the beginning you'll have lots of small splinters. You have small things that cannot be used, but it's not really bad. In practice, there is very low fragmentation when you use first fit. So it's also good. And I want to stress, maybe I said it in the beginning, in the first lecture, but I want to stress there's always a header. So whenever you're allocating an object, the system will allocate more than the space you asked for, and you will use it for its own information. So you want to allocate 24 bytes. There will be at least 8 or 16 bytes added to that will be actually allocated on the heap. And at least you want to keep the size of an object so you can free it when you need to free. And there are lots of things that are kept, all these maybe mark bits for the garbage collection or reference counting. You have in Java, you have hash info, you have locking. If you want to lock an object, Do you keep locking information? There's various stuff that you want to keep in the header, and it's always there. So assume if you're allocating some bytes, actually there'll be more bytes allocated. Okay, and now there is a coalescing thing. If you are releasing an object, there is a question if whether the space before or after it are not allocated, and then you can coalesce them into a single free space. And you can do that. Is there a picture? No. Okay, no picture. So I will do the picture. So you are freeing an object in the heap, and before it and after it, there could be free or used objects. So you want to know if you can coalesce them to a single free space. And what happens is that here you have some header with the length, and also it tells you if the object is free or not. But here you're in there's a difficulty. How will you find the header, right? The header of the previous object. Maybe you'll have to go a long way, and it will take you a lot of time to decide what is the size of this object and where it starts and whether it is in use or it is free. And so what usually is done is to keep here what is called a boundary tag. So you have a tag here that tells you the length of the object and whether it is used. The length is enough because if you have the length, you can jump to the head and see if it is used or not. So this is a boundary tag. It's like a footer instead of a header. And it tells you at least the size of the object or the space before it. And what you can do for optimization, you can say, I will live in my, so this is the space that I'm freeing in my header. I will keep a bit that tells me if the space before me is free or not. So if it's free, I want to coalesce them. Then there will be a boundary tag between it that will tell me where the beginning of the object is, and I will be able to coalesce them together as a free space. But if the object before me is in use, it is actually current, it's not a free space, then I don't need this information. I'm not going to coalesce them. In that case, I don't want to waste a full word for just telling me if it was free, where would it start? It's not free. So if it's not free, I want to allow objects to use their last word. I don't want to keep it unused. So one bit in my header will tell me if before me it is free or used. And if it is free, then there will be a boundary tag. But if not, this will be part of the used object. So I will not waste space. So this is the space optimization. Okay, yeah. This one, I coalesce these. Okay. Okay. If I'm using the optimization, I have to let the next header that this is free, but it was free previously, so I don't really need to. The length, yes, I have to change the boundary tag that tells me how long the previous object is. Yeah? Yeah. A boundary, a footer, the footer. So there is a footer here if it is not used, yes. So I don't need it anymore because it is not a footer. Now there is a larger coalesced free space, and I will put the footer here and the header here. Whatever was here is, I don't have to erase it, but I don't use it anymore. Yeah. Right. So we have here a header and the boundary tag for the free space, and the question, or even for an object, and the question is, what is the smallest object we allocate? in real life, there will be at least one word of an object and at least one word of the header. Usually it will be more, but two words is at least what you allocate usually. So it will be good enough. If it's possible to allocate just an object with a single word, then you need to do more advanced. Maybe think on how to do that more, you know, saving space. Yeah. Okay. So we have coalescing. Now, a very standard way to do best fit, and this is used a lot, is a segregated free list. So you segregate objects by their size. All the objects of size 8 are put in a list. Then all the free spaces of size 8 are in this list. Free spaces of size 24 are here, and so forth. Now, if you want to allocate an object of size 24, you come here, you take the object and you use it for allocation. If you you release space of size 16, you just add it to the list of 16. So this is easy. If you need more space, like a list is empty, you take from the end some space and add it to the free list and use it. Okay, this is a simple implementation for best fit. So, but sometimes, this is too large. If you're allowing allocations, of 2 mega, you don't want to have all the possible sizes between 1 word and 2 mega words. So sometimes what you do is you have ranges. You say, I'll have here, maybe all those between 24 and 40. They'll be in this list. Then between maybe 48 to 128 will be in this list. And then I think there is a practical variation. Yeah, each free list will have a range of sizes. And you search for a chunk in the list. You could then, inside the list, do best fit or first fit. And usually we do first fit. We look for the first thing that matches what we need, and we use it for allocation. So, and then you can ask how many lists I keep. If I have ranges, I could have large ranges and very few lists, or small ranges and many lists. Then this just you have to decide in your system what's the right way to go. We'll talk about a standard allocator and how they do this. Okay. So let's talk about specific allocators. The first allocator, and I'm saying not for garbage collection, this is for manual allocations where you do malloc and free. This was one of the first more sophisticated algorithms. No parallelism. It used to be the classical algorithm that everybody would compare to, was by Doug Lee. So let's talk about his algorithm. This was like the classic algorithm for, and everybody used it or used a small variation of it in the early days. So you have segregated free lists, as we talked about, and now you have to decide about how many cells you keep, how many lists. And he had 127, 128, approximately. The first was 16. Then, so between 16 and 512, he had one list for every size. So he says, I want to be exact on these. And after 512, he started to have ranges. So between 512 and 576, there was a single list for all this range and so forth. And until you get to 2 to the 31, which is giga. This is, yeah, 2 to the 31 is 2, but 2 giga. Yes, so this is the largest you can allocate it here, but all in 127 bins because he used ranges at higher sizes. And so this is used for best fit. almost. There is one optimization. I don't want to describe it because I want to leave time for the more sophisticated allocators. You can download it, I believe, still, and that's it. Okay. So here is a picture. You do keep. You have a status if it's free or in use. You have, if it's free, then you have pointers to the next chunk and the previous chunk. So it's a free list that is handled as a doubly linked list. At the end, you have a boundary tag that tells the size of the object, so you can merge free objects. At the end, you have this, what he calls a wilderness chunk. All the free space that you still have is at the end, and you try not to use it until you need to. So you use your lists to allocate, and only if you don't have space, then you go there and you allocate new objects for your free lists. That's it. Another allocator by Hans Baum, he did an allocator that was considered classical for garbage collection, which we'll talk about now. So what he did, here is a link if you want to download this garbage collector, okay? And he uses Mark Sweep. Okay, generational support, incremental support. I'm not going to talk about this, but we are going to talk about allocation. So here there is a similar method, but it's called block-oriented segregated list. So we have a heap, okay, and I partition the heap to blocks, and each block only allocates for a specific size. So this could be like 24, and I'll have here all the objects will be of size 24. And from my list, if I have here 24 should be here, then I have a list that goes through all the free things of size 24. I could go here and so forth. So all the objects of size 24 are allocated in pages that are devoted to sizes of 24. Okay? This is block oriented. This is a block, and each block has a size, a specific size that all the objects in the block are in that size. So the heap is partitioned to blocks, and usually a page size, 4K, and the block has only objects of that size. And when a free list is empty, you get a new block and split it. So you need, this is, I don't know, this is 64, and it's null. You don't have objects there, so you just take an additional block, and you break it into 64s, and then you link everything to this entry, and you have objects to allocate for size of 64. So when a free list is empty, you obtain a new block and you split it. Of course, when a full block is free, then you can add it to the list of free blocks. We'll soon talk how you handle free blocks. So advantages is you don't need a header for the size. You can either not have a header, or you don't need the size in the header, so you can make it shorter. You will have a word per block. You'll have some array on the size with, for each 4K bytes, you'll have a word saying this is of size 24, this is of size 16. So you don't need in the header for each object to say its size, because for the entire block it's the same size. And you don't do coalescing, so you don't need any information for that. You don't need to work on that. Just if something is freed in a 24 block, you just add it to the 24 list. That's very easy. There's reduced fragmentation. You will not get, like between blocks that you have a small space that you cannot use. 24, if it's free, you can use it. There's no, you can always use. There is some caveat to that, because if you're using like various sizes of objects, you're using one object of size 24, another object of size 100, another object of size 128. You're going to have to get blocks, but in each block you use only one word. That is going to be a waste. You'll have lots of free space in the blocks that you don't use. But usually programs do not use varying objects. They use very small number of objects, of sizes. Yeah. Right. In a page, we can only allocate sizes of 4K, maybe even 2K. We don't want to do more. So we'll have to deal with larger objects. I'll have to come to that. Yeah. Yeah, yeah. If I'm only using one object of size 24, the rest is unused. Luckily, this doesn't happen in normal programs, but you could, write a code that will do just that, and you will be very wasteful. You cannot merge different sizes. No. You're saying I allocate all of this, and then I allocate all of this, and allocate all of this, and then I release everything, so I'll have only one used in each of these pages. It doesn't have moving. Nothing moves in his space. Yes, but usually programs have a small number of sizes that they use, and they keep allocating and deleting, so you can use the free space. Yeah. I I could use ranges. No one does that. I guess you could. I don't know, somehow in practice, because a program has types of objects or classes that it uses in the class, unless it is something like a string that has varying size, a class, a student, a salary, or whatever, it has a fixed size, and you use a lot of time the same sizes. So it works very well this way. But you're right, I could do ranges. I could say, in the basically if I have 24 and before that 16, someone wants to allocate 20. Usually we allocate in multiplications of words. But if I did want to allocate 20, I would put it in a 24. That would be like an inner fragmentation. I take a larger space than I really want to for the allocation. So you're saying if I have in 16, I don't have a free list, it's empty, but I have something in 24, I could allocate in the 24. You could do that, yeah, yeah. Maybe it was tried, I don't know, but we don't do that. Uh, yeah. Right, there has to be a strategy. But saying why I'm taking a larger thing instead of opening a new one, I cannot decide that I always go for a larger, because then I will never open the 16, and maybe there will be a lot. Yeah, I agree. There has to be, I mean, it's possible and maybe it's useful in some scenarios, but you have to have a plan. You have to have an algorithm deciding how to allocate. Yes. Right. even, this is, if I allocate it here, it's 24 because this space is only for 24s. Yeah, I could allocate a 16 there, and I will not waste anything by that. But I mean, I will waste the 8 bytes, but it's possible. It wasn't done, as far as I know, in any production system. Okay, so this is the block-oriented segregated free list. Oh, the disadvantages is that you have increased fragmentation if sizes vary a lot, if you don't stick to specific sizes in your program. Okay, so block maintenance. Now I have free blocks and I want to get blocks and I want to give the allocators free blocks. And so there are 2 levels for the allocator. So free blocks are maintained in a tree sorted by the address. So if I'm looking for a block, I usually will go for the first one by the address in the tree. Sometimes I will need to allocate large objects, which is what you asked. Then I will take it from the tree of blocks. I will go over the tree of blocks and look for adjacent blocks, like consecutive space to allocate. And then I will be able to take all of them from the tree. This happens rarely. So I don't usually allocate large objects. When I do, I'll have to go through this tree and find space to allocate. Small objects are allocated inside the blocks. So this is like above some size, I go to the tree of free blocks to allocate. And with sweep, if I have a completely empty block, I find that when I do sweep. Then I add it to the tree of blocks. If I have chunks inside the block, then I just link them into the adequate entry and just add them so the allocator can use them. That's this allocate. Questions about Hans Bohm's allocator for Mark Sweep? Cool. Okay. So now the days of parallelism came and we needed to work with parallel threads. So the simplest thing is to just take this and say each thread will have this structure and its own list of chunks that it can allocate from. The blocks will be joined for all the threads. So the tree of blocks will be used by all threads and they could give back free blocks and take blocks to allocate from one another. But inside allocating small objects, you do all that locally in your structure, in your table of segregated free list. That, of course, creates more, unused spaces because, maybe I use very few, but you also use some and you use some, and each of us has its own block with free spaces. Okay, and what we're going to talk now is about the well-known allocators. So 2 of them will be for Mark Sweep, for garbage collected areas, and 2 of them will be for malloc free. And we'll see, this is what you have today if you want to implement an allocator. Okay, so the first one, I have time, cool. So the first one was done by IBM, and actually it wasn't done by researchers, it was done by practitioners. They invented this, and this is really a cool way to do it. So when you want to allocate, so you have a free list. The sweep gives you a free list. So you have this, the heap, and you have like free chunks, and you have some free list between these chunks. And all these are free objects, right? And you want to allocate, now you want to allocate an object of size 24. What do? So you could fight over the beginning of the free list and just ask for 24 bytes for your object. That will make it a lot of contention between the threads. All of them come to allocate by using the same pointer. And this is not good. This doesn't work very well. So what you do is when you want to allocate, you take a cache, like you take maybe, some block of some size, and we'll talk about the sizes soon. And this will be your local cache for allocation. And then you allocate small objects in locally inside this block. This is yours now. So you change the free list to start from here. And all of this is your local cache and you allocate in it. So you have for you, so this could be some space, I don't know, maybe 1K. And you start allocating you have this pointer that you bump, and each time you need to allocate space, you take it from your own local cache that no one touches. You took it from the free list space, and you just have your local thing, and you allocate in it all the small objects that you want to do locally with no contention. No one else is touching that cache. It's yours. And until you finish it, you work in it very fast and very local. Okay? So the advantage is there's reduced contention. You only contend with other threads when you want to get a new cache. Your cache is filled. And bump pointer allocation, if you want to allocate, you just move a pointer. That's a very fast allocation method. This is and in Mark Sweep, usually you have a free list, so you cannot use bump allocations, bump pointer allocations. So for Mark Sweep, this is an advantage. Cool. So this is the allocation cache. Using it with Mark Sweep, so Sweep creates a free list. This is very easy for Sweep. It just goes through the free chunks and threads them together into a free list like this. And to obtain a local cache, I do first fit or free list fit. I just go over the free list and find some space to get me a local cache. Okay, so I do limit, I put limits on the size of the cache that I allocate. So first of all, I don't want to get something that is too small because then I don't get the benefit. I want to be able to allocate a few objects before this is exhausted. So I don't want to get something that is too small and then compete on this pointer again. So there is a minimum size that I will take, maybe, I don't know, 1K. And there's also a maximum size. So I don't want to take all that I see to be my local cache because others will not have space. Especially in the beginning of the program, all the space is one chunk of a free list. Everything is free. I don't want to take all of it and make it my own allocation cache because then no one else will have space. So I do have a minimum and a maximum. And so they didn't say what IBM did, but they say it's about maybe at least 512 bytes, and the maximum would be maybe a mega. So you don't go beyond that, and you don't go below that, and you have, and it works very well. So the free list is if you get to a chunk and it's large, too large for the maximum allocation cache, then you cut yourself a chunk from that and leave the rest in the free list. If it is within the size of a local cache, it's between the minimum and the maximum sizes allowed, you just take the entire chunk and let the free list point to the next chunk. So, yeah.
Can a thread collect different chunks and put them together for itself and know how to distribute them back out?
Wait with back, this is when garbage collection comes. But if you want to, if you took, like this was too small and you wanted to take both from here and from here, it wouldn't be an allocation cache anymore because you couldn't just bump a pointer to allocate. You would have to know that it's not consecutive in the space, right? If this is like one chunk, you can just bump a pointer to allocate, and it's a lot easier.
But if I know to say place from then on, it's the address I bump the pointer plus a different address, then it won't be the same. Because I know, okay, I
So you do it only if you have something that is too small, right? Otherwise, you can just have one. If they are too small, then you could take more than one. They don't do it because then it's more complicated. And also, you want to work in this easy manner. And it works well. Yeah.
Everyone would take a couple of chunks to himself.
No, just an allocation cache that is part of a chunk or a full chunk, but not more than a chunk. Yeah. When you return space or when you take, if you take an allocation, when you take an allocation cache, it has to be inside a chunk. Yeah, this is similar to what bothered. This is like you will not take from two chunks and use it together for one allocation. An allocation cache. No, this is definitely not free. You know that because sweep is giving you all the free space, so there's no coalescing that you could do afterwards. This is definitely used. It was marked by the mark, and you don't have any information later if it is not if it is in use or not until you do the next mark sweep. So from your point of view, this cannot be touched. It's used. But these two are free, and this is all you can use. And so this is what you meant? Okay. Yeah. No, these are the only free chunks. You cannot add to them. Yeah. Right, the end of the cache. So I had some object to allocate and it didn't fit in the end. And I took another local cache. What do with the end? I throw it away. So we are talking about, you could save maybe space there and return it to the free list, but it's too small usually. And so on a normal basis, you would not gain anything from doing that. But there could be extreme cases where this would be the right way to go, but it's not used. Okay. Oops. So an optimization says that I don't want to keep in the free list chunks that are too small for a cache because I will never use them. They're not used for allocation directly, they're just used for caches. And so I will keep in the free list only spaces that are at least the minimum size of a cache. I just do not include, the sweep does not put in the free list any chunks that are smaller than a cache size that cannot be used. And this goes very well with the bitwise sweep. If you remember, bitwise sweep ignores small spaces. So this is really good for this type of allocation. And actually, IBM used both. So you want to keep only large blocks here that are good for allocation caches. And bitwise sweep just anyway ignores small spaces. So they go very well together. I know that some of you do not remember bitwise sweep, but when you go back on this material in the end before the test, you will remember and see that it fits. And if you ever need it. Okay, so the properties, cache behaviors, allocating sequentially, like bumping a pointer is very fast and efficiently. It's very good for locality because if you allocate things one next to each other, you also touch them many times in the order you allocate them and you have good locality. Bump pointer allocation is quick, and most allocations are local. So you don't have to synchronize, there's no contention. Usually, if you get a new cache, then you do contend. But usually you allocate from your local private cache. Emix. So we are now talking about another allocator for garbage collector. So they partition the heap. So you have like this. You have the heap, and you partition it to blocks, and each block. So the blocks are 30K, 32 kilobytes, and then you have lines of 128 bytes. Okay, this is the entire heap is partitioned to blocks, and then Each block is partitioned to lines, and you have a line map. So for each line, you have a bit telling you if it's free or not. So there is like a bit per line that tells you if it's free or not, if you can allocate on it. And the collector fills the line map. So you do mark sweep, you just mark the lines. If there's an object living in the line, you just put a bit on this line saying it's occupied, it's not free. So you have this line map, and the collector, okay. And now how do you allocate? So when you need space to allocate, and you don't have a block, you first get a block that will be your own, like you got an allocation cache, now you get a block. So you have some block, and you look for the first free line. So maybe, this is occupied, free, free, occupied, free, 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 occupied, occupied, right? You have these bits. So you look for the first line that is free, and then you look for all the consecutive lines that are free. So here you have 2, and you take this as an allocation cache. So you have space here of size of 2 lines in this case, and you just take this as a space in which you allocate. This is your allocation cache. So you search for the next free line. You group the line with all consequent free lines to form an allocation cache, and now you allocate in it. Okay, so 2 lines is 256 bytes. You just allocate in them as if it is your cache. And when you don't have free space enough in that block, you just get another block. Okay, so this is how you go. And if you have larger objects, let's start with the last line. If you have a large object, you allocate it directly from the pool of free blocks. There's a pool of free blocks, you just allocate it directly. And what happens with medium objects? If it's greater than a line, I call it medium. And now it is likely to kill the rest of my allocation cache. So I have these 2 free lines. If I try to allocate something medium in it, probably I will not have space, and then I may need to throw away the entire block. So instead of that, I keep a specialized another block. So I overflow block. I just take another block, which is maybe free or with a lot of free space. And so this is my normal block, and I have another block, which is mostly free. And medium things I allocate here, which take more than a line. I allocate in this block. So I don't kill my block, my fragmented block with larger objects, with medium-sized objects. If it's an object of size like a block or more, then I directly allocate it from the block, the free blocks. But if it is medium, then I use an overflow block to allocate that. So this is the deal with allocation. And collection, I do mark sweep. I mark objects and lines. And to sweep, all the free blocks are returned to a global pool, and partially free blocks, I have these partially free blocks. I don't have to do any free list or anything. When I want to allocate, I will take a block and I will look at the bits of the lines and I will know how to allocate in it. I don't need a free list or something. Properties. So advantages, again, you have local allocations. You have this allocation cache with the free lines. So it's bump pointer, it's good locality, and it's low synchronization, which is great. And false sharing, I will soon talk about it in our next allocator. It avoids false sharing. And basically that's it. Questions about that? Cool. So now we move to malloc free. This was with garbage collection. Now we move to malloc free. This is Horde. Horde is in Hebrew le'egor, Horde stuff. So he did his PhD in Austin with Catherine McKinley, and he started with this thing, with the Horde allocator. He he tried to do concurrent algorithms, and he implemented that, and he just couldn't get any efficiency from them. And he started studying why, and discovered that it's all about the allocations that failed him. And so he built an allocator, and his allocator Horde uh, became like a standard first allocator for parallelism. Okay, let's talk about Horde. So you can download it still. And what he wanted is to get scalability and efficiency, avoid contention. Let's talk about it. So the first thing that he found was a problem is sharing. So, and not true sharing, false sharing. Let's talk first about what is true sharing. So suppose you have a cache line. This is a cache line, true sharing. You have object A on a cache line, and two threads want to use it. And so one of them, if both want to read it, then there's no problem. The cache will go to each of these threads' lines, the cache lines, and they will use it. But if one of them wants to write it and the other one wants to write or read it, then each of these threads want this line exclusively. It wants to write into it. And then the cache line is going to move between this thread to the other thread, between one core to another. And this is called thrashing. Yes, this is the term. It's like it's going to go between one and the other, and it's going to cost a lot of time to move this cache line for one core to another. This is not good. And this happens if two threads are using very frequently the same object. Now, what could happen, and this is called false sharing, is suppose there are two objects, and thread one wants to use A and thread two wants to use B. And they don't even know that it is connected to the other objects, but somehow the allocator allocated both of them on the same cache line. Now, the computer doesn't care that it's two different objects. It's the same cache line. And it has to go from one core to another just because T1 touches A, writes to A maybe, and T2 writes or reads B. So it kind of go back and forth. It's thrashing again. And this is a false sharing. It's only sharing. They're not sharing an object. They're just sharing because the allocator decided to put the two objects on the same cache line. And this is major. So if you have something like that in your program, it will make your program run slow. I saw once people that built a garbage collector and it was slow. They didn't know why. And eventually they were very serious developers. And eventually they went to look for fault sharing. And they found out that there were structures of the garbage collectors that were just put together in the same cache lines and threads were accessing them. And when they fixed that to just not let two threads touch the same cache line, they got a 40% improvement in the performance of their system. So it was amazing. So this could be really bad. And Emery said, so also our previous collector is okay in that sense, but Emery specifically targeted this, and he says, I want to not have that. Okay. Yeah.
Does this is this created because of compaction? Because the garbage collector moves the objects to be together on the same cache line, or
It could be, but it could be. So here we don't have garbage collection. It's just malloc free, and the allocator just put them on the same line. But this could be another way that it could happen if there is a compactor that doesn't understand the relationships. So it could happen then there. Okay, so how the allocator can do fault sharing. These are slides I think that Emery gave me. So if processor one allocates some space, it takes this, it's yellow, we give colors to each process. And then the process two allocates this, then you have thrashing when they touch it because each of them is allocated on the same cache line. Cool. So this is kind of not a real evaluation or measurements, but it's the Drew. So actually, Emery came here. He gave a talk. He just came here on the day that this course was given, and He's an amazing lecturer. Did I mention that there is lecture evaluation in this course? Okay, I want to encourage you to. But in any case, at that semester, students wrote to me in the student evaluation comments that I should bring him all the time. You know, yes, I'd be happy to bring him every semester to give a lecture, like a guest lecture talk, but he doesn't come every semester, so it was only once. So he drew this line to show you that if you have some false sharing or some contention, you could start well if you have a few threads, but eventually it's going to behave badly. So performance is going to drop when you add more threads and they contend on the same cache lines. So the way he said it, when I saw this, I thought maybe I should get a real job, not just research. And I don't, he's good. You should see him once. He's on YouTube. Okay, so what can you do to solve this? You could say, let's have private local heaps, right? So they don't share the same cache line because each of them is allocating in a different location. So if he allocates, he gets this yellow object, and if he allocates again, he can get the same yellow object. But and you're sure that you will not, since you know you have some private heap, you're sure that no two threads are going to allocate it on the same line if the heaps are not sharing a line, like they're aligned to lines length. So if I free now, then I put it on my heap, right? I have local heaps. So if I free this, if he frees this, he gets it to his heap. And if he frees this, he gets it to his heap. And that creates a problem, right? Because now if they allocate, they're going to allocate on the same cache line. So if I free something and put it in my heap, and the other thread frees it and puts it on his heap, the next time in the same cache line, we can allocate two different objects on the same cache line. So how do I solve this? Yeah? Right. I put it back. It's called ownership. So this is owned by the guy who allocated it, and then I give it back to him. Okay, cool. So problem with the pure local heaps. There is another problem with if you just have local heaps where I deallocate where I free. If I have a producer consumer scenario, so someone is only allocating, the other is only freeing, then I'm going to just exhaust the heap. I'll never reuse an object, right? Because I'm allocating from my heap, but it's never freed to the same heap. It's always freed to another heap that doesn't need allocation. So I could go on forever allocating and freeing, and just my heap will be exhausted. Okay, so I need ownership, and like you said, if I allow ownership, it's not perfect, but it's good. So I could, if I allocate and this guy's free, and I allocate again and this guy's free, I can use one cell for all of this. This is like very efficient in this good case, but it's not perfect. There could be bad cases. So um, if I allocate and then he frees stuff for me, then he wants to allocate, then he needs to get from his own space to allocate. And then this guy's free, it goes back to the green one, and then he needs to allocate some new space. So if you look at this, I could use a single cell here for all the allocations and the freeing, but if I use ownership, then I need three cells for this. And if I have n processors, I will need at least, I may get a factor of n usage from what I really need. I will use more than I really need. So there, it's not perfect, but it's better. So the main ideas with these allocators, we have local heaps. They will have page size objects. Will be block oriented, like we in this well, it was like here, I have blocks of the same sized objects, and we avoid contention, avoid false sharing. Okay, we'll talk about all this. Local heaps, block-oriented segregated free lists. This is like we studied before. Um, blocks go to local heaps when fraction. So this is says I want to be able, I don't want to waste space because one thread is keeping on taking all the heaps. So if I don't have enough blocks, the number of free blocks goes down. And in my blocks, there's a lot of free objects that I'm not using, then I may take my block, although I own it, I'm giving it to the global space so others can use the free space in my block. This will get us back to maybe false sharing, but it is like a compensation between, I have to trade off between keeping my own space all the time and avoiding wasting space. So if things go wrong, I try to go the other way. Okay, so I want to allow reuse. So large objects, I go directly to the operating system. I do malloc of the operating system. I only work with small objects, which is most of the allocations. And then I go for the thread local heap. And when a block is completely free, then I can reuse the size. So if I had a block with objects of size 24, it's completely free. I can now use it to objects of size 30. That's fine. That makes sense? Yeah?
Is it the hyperconvenience of them having the sharing a heap, so why don't we make sure that they recognize that each of them has their own movable heap?
So if I have a block, right, from which I allocate, the block is mine. This is like any object that is in that block. I allocate it, someone else frees it, it will go back to the same block and it's considered mine. Unless that's how ownership is determined.
Yes, but okay, then maybe it's not relevant because the whole point of threads is that them having a shared heap so that they can all touch each other's objects. But you're saying if you're
No, I can touch them. I just don't allocate from someone else's heap. Everyone touches everything, but it's never. So if I decide to share an object with someone else and that gets me thrashing, it's my decision. It's the program. But if there are two different objects, one allocated by one thread, another allocated by another thread, I don't want to cause thrashing just because I put them on the same cache line. That I want to avoid. Whatever the program wants to do, it will do, and it can be inefficient.
touching, you just have the freeing and the not.
I just want to make sure that I allocate them to not cause problems for the program.
The local heap is only for allocations. It's not
Yeah,
okay.
yeah. Anybody can touch anything. Yeah. Okay. Here's an example that Emery did. Okay, so I have this, I'm doing malloc, I get a block, and I allocate the first object, and then I do some more. So I have all these three blocks in my heap, and I allocated all of them, and then I'm trying to free. I have a full block freed, then it can go back to the global list of pages. If I free this, and so this one can use this. If I free this, okay, if he has too many free objects, then sometimes he will go. If it's too empty, a block could go to the global pool of objects of blocks, because just there are too many free objects in my block, and I then do not want to keep them while others may need space to allocate, and I'm having all this free space. So if the free space is beyond something, so this can easily go back to the global pool because it's completely free. But maybe if a third of my block is free, this is like says, this is too much, and there are not enough blocks that can be used by the system. I give this block back as well so others can use it. And this is like a trade-off. I know that I could now get false sharing because someone will allocate on the same block, another thread may allocate on the same block, but I don't want to just keep blocks that are a third empty and I'm not using them. So there is this kind of mechanism with the right parameters, works very well. He did some comparisons. So Solaris operating system, and there was a Linux allocator and a Solaris allocator and another Solaris allocator. Compared. So this is the number of processors, and this is the speed you get, like when you run. And you see that you get a higher speed with Horde. Horde is the red line. You do manage to exploit the processors that you add. You get more speed if you add more processors. This is scalability. And the other allocators that were there in 2000 did not do well. In this benchmark, they really did not do well, and he did well. And so it was a very good allocator, and it was used for a long time. And sometimes so he compared to Doug Lee, which was the classical algorithm at that time. And he says he needed more space because of all his structures, but normally not more than 20% more space. So this is what he says about fragmentation. Questions about Horde? Okay, our final collector is what you would want to use today if you allocated. This is the latest. This is from Microsoft Malloc. So what did he do? He said, let's not have a general free list, but let's break. So we now break the heap into size 64 kilobytes. Okay, so we have these 64 kilobytes, and now a free list is separated for each of these blocks. So I have a free list, and also so I do have these sizes. So for each size, I will have a separate list. So I have here says 18, and this is of size all 18, 24. Let's make it divisible by 8. So all the objects here are 24. These are the objects here, but there is a specific free list for this block. Right? You don't go with a free list over different blocks. There's just, this one is free, this one is free, that one is free. This is the free list of this block. And until you exhaust this block, you don't go to other blocks. So you keep on the same space. Your locality is better. Okay, for each size class, you have a current block that you're using, a page that you're using. So I, as a thread, I have this list of all sizes that I'm allocating. And for each size, I just have such a block. So I have a free list of that block. And the one thing is that all allocations will be close together in memory because they will be in the same block. And also the freed, everything that is freed immediately will be added to my free list so I can use it. So while I'm allocating from this, some objects get freed. We were talking about malloc free. So all the time things get free and they will just be added to my list and I can use them. And to reduce contention, I'll have two free lists. I have my local free list, and then there will be a global free list. So if I'm allocating from my local free list, and I can also free into my local free list. So I can add and remove things from the free list. If other threads are freeing in that block, then they're going to add their freed objects, spaces, to the global free list. Now, if I'm done, if my local free list is empty, I will take the global free list and add it to my local free list. And then I very seldom, only when I do that, I have to compete with other threads and contend and synchronize with them. Otherwise, I'm working locally without any contention. So this is the basic way. He calls it free list sharding. I'm just breaking the free list into lots of smaller free lists. And this is the main thing that gave it the great behavior.
The freelance is also per minimal page, right?
Yes. Global means for shared by all the threads. Local means I only touch it. Yes. Okay. So here is a drawing by Dan. So this is if this is like a regular. This is the free list. So what could happen is that new allocations can happen. So you can have maybe you allocating a linked list. It could go, to all kinds of spaces in the memory, and your allocation could be all over the memory, right? And when he allocates in his, so you know that you'll first use all the objects in the same block and only then go to a different block. So things that you allocate are going to be near each other in the memory. Okay, so to reduce synchronization, you use these two free lists, the local free list, you locally free and you locally allocate. And the global free list is that other threads can free. They don't allocate from your block, but they can free stuff that you will be able to use. Okay, so these are all words of Dan. You think of industry approach. So you have large and widely used services, and this is this is very much what interests the large companies. Data centers, powerful machines, hundreds of threads, very large memories, and instead of and you care a lot for the services, the latency. So how much time does it take to answer a question of the user? And usually they say they're not willing to let it linger for a long while. They really want it to be short. And the way they say it, they say, maybe for 1 of 1,000, I allow you to take, I don't know, a second. But for all the other 999 requests, I want you to answer within 1 millisecond. So there is, I really want it to be fast and steady. So for example, this is usually considered bad. If these are the answer times and you have like once in 5 requests, you suddenly have a 6x, like a factor large time to respond, it's worse than to have a very steady good pace in responding, and you don't have these unhappy clients that have to wait 6 times as the others. So okay, I will skip all these examples by Dan, but this is what happened when they inserted his memalloc. So they had these big machines running with the previous specifically designed allocations for their application. And this was the way it behaved also with these spikes. And then they added his allocator and it became a lot faster. And it was surprising at how much it behaved well. It is like less than 10,000 lines of code for his allocator. Before that, they had maybe 100,000 lines of code for the specific things that they did. It's really general and not too sophisticated, and it works amazingly. And mostly because it stays on the same block, which is quite amazing. I mean, he also implements very well. He's a very good implementer, but the ideas were nice. So he compares to tcmalloc by Google, jmalloc by Facebook, and TBB by Intel. And this is the comparison, various benchmarks. And You see how much this is relative time, lower is better. And so mimalok is the first one. And you have the others, and you can see that mimalok behaves better everywhere, basically. No one beats him. And this is benchmark one, benchmark two. So these benchmarks are sometimes proprietary of these companies. They cannot be put out of the company because of secrecy, but he measured it. And this is so this is very good behavior. So to summarize of what we studied, we talked about fragmentation, we talked about some basic notions and techniques, and then Doug Lee and Bohm were the first to work with, not the first, but the first classical collectors to work with malloc-free and garbage collection. And then we talked about two garbage collected environment allocators that work with Mark Sweep very well, and then two allocators that work with malloc-free. Yes.
התייחסנו בכלל לקומפקשן, זה כל כאילו אם אנחנו רוצים, הוא יותר נכון אולי זה קשור למרקינג סוויפ, G7, שכאילו איך אנחנו עושים, איך אנחנו מתייחסים לקומפקשן שאנחנו מגיבים אחרי זה, דברים כאלה, מה עושים?
So with malloc-free you do not compact. There's no way for you to know the pointers to an object, and you cannot, it's not managed, you cannot compact. If you work with Mark Sweep, then you allocate. If you need to compact later, it's orthogonal. You don't. Usually, our compaction algorithms went by the same order that the objects were allocated. So if you allocated them near each other, they stay near each other, but in a more compact space. Other than that, there's no further connection between the allocator and the compactor. So that's it. Maybe there is a way to do something better, but it wasn't done, and I don't see immediately how to do something like that. Okay, so we have 10 minutes just to summarize. I want to go over the right barriers that we had, and through them, just that you'll have them organized in your head, and through them to understand some of the algorithms. So when we talk about the right barrier, we have some pointer that is written, and there was an old object that was pointed by the pointer, and there is a new or target object. Okay, and now you have to decide what to do. And I'll go through each of these, but Dijkstra says we shade the new or the target, and then you could grade the parent. Mostly concurrent says, you know, if I change something, I want you to look at it again. This was the mostly concurrent collector. Then there was a snapshot the parent, like we did with reference counting. We said, if something changes, I want to keep its original state in some buffers. Actually, let's go over each of them. So if you recall, Dijkstra said, I could let the collector know about the new object or the old object or the parent that was modified. And Dijkstra said, you know, I'm going to let the collector know about the new objects that gets pointers. And Dijkstra could only work with a single mutator, single program thread because of that. And basically, I don't think there was a later research that did better, like that used this right barrier and did multiple threads. I think it's possible, but it was not done. And Dijkstra says if it's atomic, you just don't have black to white edges. If it's not atomic, we have this analysis showing that it's okay. It still works well for a single thread. Then there was mostly concurrent. If you remember, we said there was dirty cards. Whenever you change a pointer, You want to say, maybe I didn't trace this guy properly. I will not trace this guy properly. So I'm going to dirty the card, which basically says that I'm graying the parent. I make you go over it again. And this is this was the second way to do right barrier and to tell the collector what you want, what you change, and how he should behave with it. Um, Termination is a problem because things changing all the time, and you get more and more gray objects. And so, at some point, you need to stop the activity of the program and just finish all these dirty cards that we had in mostly concurrent or gray objects that are created while the program is running. So this seems to require, in order to finish, you need to do a stop the world phase at the end. Then we had things like, so in the reference counting, in the also mark sweep, that we had a barrier that said, when I change this pointer, I remember how the parent looked like before the change. So we had this Lebanoni right barrier that says you just keep the original value and you trace from that. And that gives you a snapshot. Like in the beginning, you just start this right barrier, and then anything that changes, you're going to traverse the old way it was. And if it changes a lot of time during the collections, you're going to always have the first one that was in the snapshot. So you can really traverse the heap as if you're looking at it during the snapshot time in the beginning. This is called snapshot at the beginning. And this allows accurate mark sweep at the snapshot time and also allows doing reference counting. You can do concurrent reference counting using this right barrier. So this was snapshotting the parent. You could also just remember the old value, not remember what the parent looked like, remember the old value. So if you have many changes to a pointer, all of these are going to remembered because each time someone loses a pointer, you're going to add it to your list of old values. In contrast to remembering the parent, where you only once keep the parent when it is first changed, and then you see only A. If you just notify the collector about the old values, if you change it many times, you're going to record all these objects that lost a parent. So you will traverse a snapshot, like a superset of the snapshot, but you will add additional pointers that you don't need to look at. So this is the third right barrier. And you could, this is the fourth right barrier. And this is just to tell you that you can, when you change a pointer, you have to tell the collector you did it, because otherwise you cannot traverse a graph and find all the reachable objects. You could tell him about the new objects, the old objects, the original parent object. Just tell him to retraverse the parent. These are the things that we've seen in all our concurrent collectors. So that's it. Questions about the right barrier? No, okay. You know everything. Thank you very much. See you next week.